Alright, we're up and live. Cool. So any questions to begin with? If you've got issues with PA1, this is a really good opportunity to talk about those.
We get a lot of errors using valgrind plays and search, so I'm kind of curious from like how, can you kind of explain the idea behind using search?
Are the errors related to your search algorithm, or are you getting valgrind errors about uninitialized things with lots of hex numbers and stuff like that?
It's mostly using search function, because every time I call add, it goes to my search function, but it doesn't, but for some reason, there's some kind of error going on. I'm trying to go to Office Hours tomorrow to explain more in detail.
Okay, but can you tell me more about these errors? These are valgrind errors?
Yeah.
So valgrind errors don't usually have a lot to do with your algorithm itself. It has to do with your implementation of your algorithm in code. So let me show you an example here, because I really do want people to get rid of their errors. So let's see. What can we do here? That didn't work. Trying to reproduce the most common error, and surprisingly it's difficult to reproduce. Okay, let's see. So I'm guessing you're seeing errors like this, where it talks about conditional jump or move depends on uninitialized values.
Yeah, that's okay.
Okay. So those are going to pop up a lot, and like I say, your code might exhibit these errors, and it still might work perfectly, but it's still an issue. So if you just compile in the usual way and run, you get these messages, and it tells you it's happening inside add, it's happening inside main. So the first thing is compile with the -G switch, as if you were going to debug. And when valgrind gives you these messages, it will usually pin them down. For example, it's telling me line 28 of main, line 17 of main. Alright, so conditional jump or move depends on uninitialized values. So it's at my add function, it's at line 28 of main, and it was called from main, line 17. So line 17 called add, and add had a problem at line 28. So go in here to line 17, there's my call to add. Go down to 28, here's the statement that's causing that message. And the message actually says uninitialized value or values. And what's happening in this case is I'm looking at the next field of my Sentinel node, and I have never assigned a value there. So take a look at exactly what our code says. Our main program says the following: sent equals malloc. Okay, when we call malloc, we're creating a box. It's got two spots, one for a number, one for a pointer. We're calling it sent. Okay, that's the picture that goes along with this first statement of C code. And now I'm calling the add function. and I come into my add function. I'm passing it sentinel, so sentinel is the address of this box. And I have this statement, if sent arrow next equals null. So when the code tries to look at the value of sent arrow next, it says, okay, sent is a pointer. Let's find the thing it points to. That's this box. Let's look at the field called next and see what the value is there. It hasn't been initialized. And that's a huge problem. Now, we may luck out and it may end up being 0, and 0 happens to be the value of null, but that's just sheer luck. The reality is we're comparing this to see if it's null because we want to know if there's another node after this, but we haven't initialized this to be null. And so every time you get a message like that about uninitialized values, it's a warning that you've forgotten to initialize something. So if I do the following, if I set my sentinel node up, and let's go ahead and set the number to some value, and let's set the next node equal to null, that'll get rid of that warning. And now I'm back to nice and clean. So that would be the thing to look at and take care of as far as the valgrind issues. As far as if the search function is not working, that's a thing to look at, yeah, probably in office hours. But I would say, you know, look at your list in GDB, make sure that the data you're looking for is actually stored in this link of nodes. And then GDB your search function one step at a time. And either it's giving up too quickly, or it's not recognizing when it gets to the node that it should be recognizing, or it's doing something really wacky, like it's using the wrong sentinel node and it's not even looking at the right list. But going into GDB using print statements and so on and so forth will help you figure out at least which of those categories you're in, and hopefully drill down to the exact problem. And that's something that we can do in office hours to practice with GDB. Let's see, could we do a bit of a review of makefiles, especially with chain rules and implicit chain rules, like how make interacts with intermediate objects? I don't even know what chain rules or implicit chain rules are, so I certainly cannot review those. But I can show you a sample makefile, and that may help. Let's see. So here's a makefile from PA3 last quarter. So, you know, have the name of your main target that you want to build, colon, and then a list of the things that depends on. To build my main executable, which is called main, all I need is my object files, my .os. And if all of those are present and up to date, the command I used to build my main program in this case was gcc-o, output file, and then the names of the objects, and a -lm. We don't need -lm for PA1, don't put that in, I'll take off points. But, you know, put in the gcc command that links the .o files together into an executable. And then each of those object files, the .os, list what they depend on. So for example, getAnswer.o depended only on getAnswer.c, whereas main.o depends on main.c and also main.h. Because main.c presumably includes main.h, whereas getAnswer.c doesn't. And so for each of these intermediate targets, these .o files, these objects, list the files that they depend on, the files that have to be up to date, and then if they're present, we can use this gcc command to compile this file into this object. So this will compile main.c into main.o. Intro.c gets compiled into intro.o, and so on. And then the clean target is kind of a bogus target. It has no dependencies, and it just removes the executable and all of the objects that we compiled. Can you explain what our makefile should do to earn full points? Sure. So basically, if I change one file, if I change main.c and I say make, it should recompile main.c. It should not recompile functions.c. If I only change functions.c and I say make, it should only recompile functions.c. If I change main.h and I say make, it should probably recompile both of those, assuming that they both include main.h. And if I say make and it builds my executable, if I say make again without changing anything, it should not recompile anything. It should say all files are up to date. So that's two of the requirements. The first is to be tactical about what you compile. Only compile things that need to be recompiled, i.e. things that have changed or depend on things that change. Compile everything to objects and link those objects together. And then the third requirement, make sure you have a clean target. So if you say make clean, it'll remove all the stuff that was built by your makefile, or potentially built by your makefile. And let's see, yeah, go ahead.
Will a -G flag socket points?
No, you can put a -G in there if you want. That's fine. I don't mind if you build with the G switch on. So for make clean, I would not do star.o and star.c, because imagine that you downloaded this package and you're trying to build it, right? And maybe you've got your own test program that you're developing to work with this. Well, if your make clean just removes all the .o files, it might wipe out files that you created and compiled and so on. And you definitely don't want to delete all the star.c files. And you can't combine your make file into a single line by doing star.c and star.o and so on. You need a separate list of dependencies and recipe for each piece of the project. Yeah. So you should be able to just say make, and it should make whatever the first target is, and the first target should be main, and that should build your whole executable. Let's see, you can explain what are makefiles. Can you review sorting or where to add a node? Add the node in increasing order. So, alright, so what are we talking about? Makefiles. Sort order. So you're not sorting your list, you're inserting in sorted order. So if your list contains a 10 and a 20 and a 30, and you say add 25, the 25 should go right here, so that your new list is 10, 20, 25, 30. So you don't actually do a sort on the nodes in the list. But when you insert something, if I say add a 6, it should insert it in the right spot in this already sorted list to keep the list sorted. So if I say add 6, that 6 should just go in the beginning. So that's the sense in which we're sorting. Is the setting of the sentinel data and next node value supposed to happen in a init or main? Definitely in a init. Your main program should never manipulate the sentinel node. It simply calls a init and saves the value that comes back in a variable that you call mylist. But setting up that magic value for data and setting the next field to be null, do that in a init. And this is the idea of an abstract data type, right? For some reason, you're supposed to have a data value of 1, 2, 3, 4, 5, 6, 7 in the Sentinel node. That's definitely not something that you need the user to worry about, and you don't want the user to worry about, right? You don't want to give the user a package and say, by the way, every time you create a linked list, make sure you set the data value to 1, 2, 3, 4, 5, 6, 7. That would be kind of a weird package, right? So that's something that should be taken care of by your linked list functions, in particular the init function. So that's that separation of user code from the implementation of the linked list. Will there be in-person learning next week? I will make a decision at the end of this week. But I just got case numbers yesterday, and we're up 420% from the week before as far as active cases, which is not terribly encouraging. You know, state government has gone completely remote. Public schools are going remote. More and more colleges and universities are going remote. So I don't know. I'm unsure at this point. I'm really anxious to get into the classroom, but I'm feeling like it's really it's a needless risk to ask people to take, and frankly to put myself in also. To say, yeah, let's you know, hop in when we're getting, you know, 1,000 new cases a day in Clark County and 46,000 new cases a day in the state, and you know, 1 million in the country. So I'll make a decision in the next couple of days, and again I'll post on Canvas. But we'll see what happens. And that's just speaking for this class. For the rest of the campus, I have no idea. Right now the plan is they're trying to keep the campus open, but they're also telling faculty to be prepared if needed to switch to entirely remote or online. So I don't know which way that's going to go. Can I show you my makefile? It works and does what it's supposed to, but I want to make sure it's okay for this assignment. Yeah, you can hop into office hours and show me your makefile, and I'll give you a thumbs up or thumbs down and let you know if there's something missing and such. Let's see, not encouraging given how infectious it is, not surprising either, unfortunately. Band director's out sick. Oh no. That's unfortunate. I really wanted to join the orchestra this year. And I was just gonna like go for it, but I just couldn't bring myself to do it with in-person rehearsals. Also had a question about the Sentinel setup in chat. Where's the Sentinel setup question? I don't see a question in chat about Sentinel setup, so maybe you can resend it. Or repost it. Is setting of the Sentinel data and next value supposed to happen in init or main? Definitely in init. I actually railed about that for like 2 minutes when I read it a little while ago. So I don't know if you missed that. But yes, always, always, always in init. Go back to the recording and catch my little 2-minute rant on it, because it's really, really important that you don't monkey with the Sentinel node's details in main. Right? It's got to be done in the init function. Yeah, my test code is just junk code though, right? And I've tried to make it clear from the beginning, when we're writing test code, it probably has nothing to do with the requirements of the assignment that we're currently working on, right? We're just, you know, writing test code, and when you write test code, you should totally ignore the requirements of the assignment that you're working on. Don't, you know, if you're trying to write test code to put some nodes together and follow them in GDB, don't force yourself to, you know, make a separate functions.c and a makefile and, you know, name it this and that and so on and so forth, right? Quick and dirty test code is your friend. Get in there and write some code and look at it and figure out, you know, what's going on. That's your business, right? You do that however you like, and my suggestion would be do it in the way that's quickest and easiest and most straightforward for you. When you're turning in PA1, I got all kinds of weird requirements in there, right, which I'm putting in for reasons, but you know, they're extra things you're going to have to do. But that's, you know, that's the version that you're turning in. When you're writing a book, you know, and you send it to your publisher, it's got to follow certain formatting requirements and so on. When you're sketching out your storyline, you grab a napkin and you start, you know, scribbling fragments of sentences. So that's what I mean by junk code, right? It's not worthless code. It's code that you're just, you know, putting together to do something else, to figure out some concept or something. All right, all excellent questions. Other stuff. All right. Well, we are going to leave our discussion of implementing linked lists in PA1 for a bit, and we're going to go on to a new pair of data structures. And these are stacks and queues. And when we come back to implementing stacks and queues, one way we'll do this is with linked lists. And I may do your second programming assignment on stacks and queues, in which case you'll get to use your linked list package in PA2, but I won't pin down PA2 until next week probably. But let's talk about stacks and queues, and let's begin with stacks, because they're a little more familiar to us maybe. So a stack, right, is a place where you can store a bunch of stuff. And then you can retrieve this stuff that you've stored later on. And so, you know, if this was a stack, I could store, you know, a napkin, and I could store a pen, and I could store a pair of cufflinks. Now, if I store this in a stack, there's a very particular way that I retrieve these things. I retrieve them in the opposite order in which I stored them. So if I stored a napkin, and then I stored a pen, and then I stored a pair of cufflinks, and now I go to the stack and I say, hey, give me something back, it's going to give me the last thing that I stored. It's going to give me that. Now if I say, give me something else, it's going to give me the next to the last thing that I stored. And now if I say, give me something else, it's going to give me the first thing that I stored. Alright, and if I store a napkin, and then I store a pen, and then I store cufflinks, and I say, give me something I stored, and it gives me that last thing I stored, which is the cufflinks. And now I say, you know, I want to store my Hello Kitty stickers. And now I say, give me the last thing I stored, it's going to give me back the Hello Kitty stickers. And now if I say, give me the last thing, it'll give me the pen finally. And at this point, if I say, hey, store a mouse, right, it stores a mouse. And now if I say, give me the last thing I stored, it gives me back the mouse. This poor napkin, the first thing I put in my stack, I'm not going to get that back until I've gotten everything else back that I stored after it. Alright, so you got the basic flow of things here. And this has got the structure of a last in, first out, or what's called a LIFO. The last thing you store in the stack will be the first thing that gets removed from the stack. And so you can also think of this as you know, a pile or a stack of things on your desk. So if you start piling up, you know, books on your desk, you put down a first book, a second book, a third book, a fourth book. Unless you want to play Jenga, right, the first thing you're going to remove is the book that's on the top. That's the one that you just put there, that's the one you're going to take off. And now you've got 3 books left, and the next one you're going to remove is the one that's at the top of that shorter pile. So let's say we put down a book A, and B, and C, and D. So this is a stack. And we can call this end, you know, where you put the last thing, we can call that the top of the stack. And it's often just called TOS, top of stack. And with a stack, nothing ever happens to anything that's not at the top. we're not going to go in and pull this book B out from the middle of the stack. But we can do two things. We can add something new on top of the stack. We could put another book up here, E, or we could remove what's at the top of the stack, get rid of that D, and now C would be the top of the stack. All right, ask questions if this isn't making sense. I'll take silence as like understanding. So we have two operations. We have a push and we have a pop. When we push something, that means add to the stack. When we pop, that means remove from stack.
Does that stand for like pull out of? Oh. What does that stand for?
What does what stand for?
Pop.
Oh, you know, like popping the top off a bottle of soda.
Okay.
So just literally that.
That's the same notation as JavaScript. You pop and push.
Yeah, yeah. It's pretty standardized. So pushing means, you know, put something new on the top of the stack. So if I were to push a book E, right, then E would sit up here. And the top of the stack would now be here. If I say pop, it's going to remove this thing from the stack. Pop will usually give you back, you know, the thing that was removed, so that would give me back book E, and now this is the top of the stack. And if I pop again, that would give me a D, and now this would be the top of the stack.
So there would be no point in identifying what you want to pop, because it's always going to pop the last in.
It's always going to pop the last in, yeah. So a pure stack, you can't say pop, you know, the thing, two things below the top of the stack. That's not really allowed. But some stacks will let you do that. All right, so two things can happen. If I pop off the C and I pop off the B, so that A is the top of the stack, and then I pop off the A, right, my stack can be empty. And so the top of the stack would be, I don't know, you know, like the surface of my desk or something. It's an empty stack. And if I were to push something on there, it would become the first thing on the stack. So empty stacks are fine, but if I have an empty stack and I try to pop, that's an error. I'm saying, give me, say again?
Is it possible to make more than one stack? Just out of curiosity.
Sure, you'll typically have a lot of stacks in a program or in an operating system. Yeah, that would be useful. So if you try to pop from an empty stack, that gives you an error called a stack underflow. Stack underflow just means exactly that. It means you pop from an empty stack.
So what's stack overflow?
Stack overflow is when your stack is full. So your stack can be full. And it depends how your stack's implemented. If you implement a stack in some ways, you might have to decide, you know, the stack can only hold 1,000 things. If you implement a stack other ways, you can say the stack can hold as much as we have memory available on the system. But there's always a limit with a physical computer to how much stuff you can store on the stack. And so if you push to a full stack, that's your famous stack overflow. And if you go to the Stack Overflow site, come on. Wow. spelling it wrong. Or maybe my network is just hosed. Oh, well, this is interesting. Well, I'm guessing I'm going to lose my Zoom connection in a minute. Testing 1, 2, 3. Are you out there?
Yeah,
Yeah, me too.
it says I'm connected though.
Yeah.
Okay.
Well, let's see.
Yeah, I'm still out.
Yeah. Well, that's good fun. Alright, we'll keep the live recording running.
We got uplink.
We got that going. Unknown error occurred. Connecting.
Yeah, same internet.
Yeah. Well, that was timely. Hey, maybe we're back.
You got back, I think.
Alright, I am back.
Did he? Yeah, he's in the fixing that he's mixing a host.
Alright, yeah, I'm back.
Dang it.
So, yeah, maybe.
So like where you got somehow you made me host and I got kicked off at then like
Okay.
hey, what's this screen share this and that.
Nice. Yeah, I think you're first alphabetically, so.
I blame you unofficially.
Maybe we came up with the idea. He even posted a link to some pirated anime website.
Alright. Alright, cool. Well, we are back. We got a screen share going. Yeah, that was weird.
Can you answer the question about what's stackable flow?
So how far did we get? Did I talk did
You not even one syllable. Yeah, not even one syllable.
not even one syllable. All right. Well, we will do this again then. So your stack can be full, and so depending on how you implement it, you make a decision up front. For example, you might say my stack can hold 1,000 entries, or you might implement a stack that can use all the memory available on the machine. But there's always some limit to how much a stack can hold. And if you put in too much stuff to your stack becomes full. And then if you push to a full stack, that gives you a stack overflow. And it's basically saying there's no room to store anything else on the stack. Does that make sense?
Yeah.
And so the Stack Overflow site, right? There's their icon, and it's, you know, a little tray that holds things, and you put too many things in there, and the stack falls over, right? So that's a visual representation of a Stack Overflow. Or, you know, you're piling books on your desk, and you pile it as high as you can, and you try to put one more, and now the whole thing, you know, comes crashing down. Or you've piled it all the way to the ceiling, and there's no room to put another book in. Alright, so that explanation is on the recording twice now. So there's a blip in the recording. Alright, so that's a stack, right? And what do we want to do with a stack? So let's think about a stack as an abstract data type, an ADT. So what do you do with a stack? Well, you need some way to initialize a stack. So you want to create an empty stack and do whatever setup has to be done. You can push to a stack. You can pop from a stack. And maybe you want, you know, some functions to let you know the status of the stack. So you could have a function which says, is the stack empty? And another function which says, is the stack full? And maybe you could have some other functions like, clear, which says get rid of everything on the stack and just give me an empty stack. And there might be other functions as well. But this would define, the interface between a user program or a main program and the implementation of a stack. And so if you wanted to do something like make a calculator program, calculator programs are pretty simple if you have access to a stack. And so your main program would call a init to create a stack, and it would process user input, and it would do pushes and pops and so on and so forth. But your main program wouldn't really care how the stack is implemented. And it could be implemented in a number of ways. It could be implemented with an array, it could be implemented with a linked list, it could be implemented with somebody writing things on pieces of paper and piling them on top of one another. As long as the interface is well defined, your main program doesn't need to worry about how the stack is implemented. How are we getting this first in, last out, or last in, first out behavior? So this is another example of this idea of an abstract data type. This sense that we would write a package that implements some set of functions, and we would ask the main program to call those functions to interact with the stack. And all the low-level details of what happens when we do a push, what happens when we do a pop, and so on, those are handled by the implementation of the stack package. Making sense so far?
Yeah.
So if we want to implement a linked list, one way, a stack, one way to do that is with a linked list. And in fact, we started to do this the other day when we made our slightly simpler add function. And we noticed that, when we made our add function that always added right after the Sentinel node, and we added a 10, a 20, and a 30, and then we printed the list, the numbers came out in reverse order. And that's the nature of a linked list, where you insert after the Sentinel. So imagine that we're going to make a push function, which simply takes this number and adds it to the beginning of a linked list. So we'll start off with an empty list, which is just a Sentinel. When we say push 10, we'll have the Sentinel point to a 10. When we say push 20, we'll change the Sentinel to point to a 20 and have that point to a 10. When we say push 30, we'll add a 30, have the Sentinel point to that, and have the 30 point to the previous head. So this is our stack, right? It's a 30 followed by a 20 followed by a 10. And now when we say pop, what we would do is we would remove the first node from the list. So it's like a delete, that instead of deleting a particular number, it deletes a particular position. In this case, the first position in the list. So how would we code a delete function? Well, see what the Sentinel points to, return the data value of that node, and change the Sentinel to point to the second node and free that first node from memory. Let me see what chat's saying here. Yeah, I actually wondered if there was a Stack Overflow at Comcast or something. That would be like awesome. Alright, so push, insert at the start of the list, pop, delete from the start of the list. So the push function, we actually wrote that the other day when we wrote our simpler add function. The pop function would basically do something like, temp equals sentinel next. Temp data equals the temporary node's data field, right? So temp will be this thing that the sentinel's pointing to. Temp data would be the number value from there. And then we change sentinel next to be whatever temp was pointing to. So now the sentinel points to what this first node's pointing to. The sentinel will point to 20. And then we can free the temp node to release this from the memory pool and then return temp data. So there's pseudocode for a pop function. And the weird thing in here is, the slightly weird thing in here is that, I'm using these temporary variables. Why am I doing that? I'm going to free my temp node down here, which means once I free my temp node, I can't see what its data value is, so I have to save that data value somewhere. So I'm setting up, a temporary to point to that first node, and I'm saving its data value in just a plain old integer, so that I can return that even after I freed this node pointer. And really the only sort of action items here are this and this, right? Have the sentinel point to the second node of the list and return the data value of what was the first node. So what could cause this pseudocode to blow up? How could we get into trouble with this? Where's the seg fault potential?
Doesn't check for empty.
Yeah. Because if our sentinel is pointing to null, temp is going to be null. This is going to be a seg fault right here. This is going to be a seg fault. This is going to be a seg fault. We're going to seg fault all over the place. I mean, first seg fault exits, but we've got lots of things going on. So we need to do a special check here, right? If temp is null. Well, what does that mean? If temp is null, it means the sentinel wasn't pointing to anything. That means your stack was empty. And so this is a stack underflow. So we actually need to check for that condition when we're implementing this in order to avoid probable seg faults. What's the counterpoint? Where would a stack overflow kick in?
On the push, but we didn't.
On the push, which we haven't written out code for, but do I have it in here? Right, in our add function, we call malloc. And, you're supposed to check the return value from malloc anytime you call it and see if it's null. If it is, that means you are out of memory. So I should have something in here which checks to see if temp is null after I make this call. And if it is, I've got a stack overflow. I'm out of memory. And I should do something appropriate. What should I do? I don't know. I mean, one thing you can do is you can have, your push function return a status flag, which is 1 if it exceeds, 0 if it runs out of memory. Or you can just seg fault and, let the user's program blow up. It depends on your implementation goals. So I'm saying you don't need to check the return from malloc in the init function. because there's no way for init to let you know that you're out of memory. So we're just going to assume when you call init that everything is fine. But your add function definitely checks for out of memory, and returns a 0 if it's unable to add your number because of that. So yeah, you're square. All right, so that's an implementation with a linked list. And it's not that hard to implement once you have, you know, the mechanics of a linked list pretty square in your mind. The push is what we already did, and the pop is you know, just implementing this. All right, questions about that?
I noticed that you have the case where some number n equals pop. If that was the case, how would you know if pop was an error?
Well, that's a good question too. So how would we detect the stack underflow? And you know, a lot of stack packages will simply throw an exception if you underflow, and it's up to the user to make sure that doesn't happen. Now, a well-written program probably should never underflow. You should know what's on the stack. You shouldn't just keep popping randomly. But if you have something like an isEmpty function that will tell you whether or not there's anything on the stack, you can just call that before you call the pop.
Oh, I forgot it's empty.
Yeah, and how do you know if it's empty? Well, just check to see if the sentinel's pointing to null. So that's a pretty simple function to wire up. But yeah, if you're returning an integer here, then there's no way to indicate a flag, you know, saying that that you had a stack underflow. So you could do that. I mean, you could return a structure that could contain, you know, the integer value and also a flag saying success or underflow, things like that. But the stack underflows usually aren't a problem unless there's an issue with the program. Stack overflows are the ones that you know are hard to avoid if you just consume more and more memory, which happens sometimes. All right, so why do we care about stacks? They have this peculiar last in, first out, or you know, sometimes first in, last out, but don't ever use that in an interview, right? Pretty much everybody calls these things LIFOs, and if you call it a phyllo, you're going to think you're like a pastry baker or something, like phyllo dough. But you know, same idea, first in, last out, last in, first out, but this is the one we usually use. So what is it about this structure that the last thing you put in is the first thing that you take out? It turns out to be kind of parallel to the way that most people structure tasks throughout their day. For example, let's say you're doing your homework. So your task is to do your homework. Well, you can't do your homework until you get some paper. So you have to get some paper. And when you go to get some paper, you realize there is no paper, so you have to go to the store to get your paper. And while you're driving to the store, you realize you're almost out of gas, so you have to stop to get gas. Right? And so the way I'm writing this, our stack is growing in this direction, the top of stack is at the bottom of the page. And when you deal with stacks, you'll see all sorts of ways that they're represented in data sheets, in textbooks, and so on. In this case, I'm growing the stack from top to bottom, and so the top of the stack's at the bottom of the page, right? So you got to be clear what way your documentation is drawing the stack. So if this is the top of the stack, this is the bottom of the stack, right? Our poor homework assignment is at the bottom of the stack. It's the last thing we're going to do, right? Because it's the first thing we put on our stack. And we're not going to get to doing our homework until we get paper. We're not going to get paper until we've gone shopping at the store. And we're not going to get to the store until we get gas. And you know, if I want to get gas, well, first I got to stop at the ATM and I got to get money. And I can't get money until I find an ATM. So I'm going to take out my phone and start Googling where's the nearest ATM. Well, my battery's dead, so I've got to charge my phone. And this is how most of us live our lives, or a lot of us, right? We have this big to-do list in our head. And the thing that we really wanted to do is kind of at the bottom of that list, right? And we got these other things we've got to do first. And so, you know, we'll charge our phone, we'll pop that off the stack, we'll find an ATM, pop that off. We'll get to the ATM, get some money, pop that off, get our gas, get to the store, and while we're at the store, maybe we remember, oh, we have to buy food. Because I forgot I didn't have any food in the house. So now I'm buying food, you know, and when I'm done buying food, I finish, you know, getting my paper, I'm done with going to the store, I'm done with getting the paper, I'm ready to do my homework. Well, now I'm hungry, so I have to, like, you know, eat food. And while I'm cooking my food, I want some music, so first I'm going to put on music. Right? So this is this last in, first out. We keep coming up with new tasks, and the task we just came up with, that's the thing we're doing. And so I put on music, and I finish making my food, and I eat it, and now I'm ready to do my homework. You know, but I'm bored already, so I'm gonna go play Steam to like relax before I get into my homework. And so on and so forth. And so when we're organizing tasks, we often do this with a stack-like structure. And it turns out, maybe for that reason, computers do exactly the same thing. So like people, computers often work with a LIFO structure. And one way that we see this is when we think about functions and making function calls. So here's the operating system. This is bash. And you type in the name of your program, and bash makes a call to a function named main inside your program's executable file. And main makes a function call to init. And init makes a function call to malloc. So when this call to malloc is executing, the computer needs to remember, hey, I was doing init. I want to go back and finish doing init. But right now I'm doing malloc. I'm running this code that asks the operating system for a chunk of memory. But it needs to remember, hey, I was in the middle of this function init. I was at line 5, which called malloc. And when I'm done with this call to malloc, I need to go back to line 6. And I need to load 1, 2, 3, 4, 5, 6, 7 into data and null into the next field, and so on. And when I'm done with init, I need to know, hey, I was in the middle of my main program. And I was at line 17 when I called init, and so I need to go back to line 18 of main, and I need to print out a prompt and wait for the user to do stuff. And somewhere in main, you know, the user's going to type in X, and you're going to free memory, and you're going to say return. And what happens after the main program returns? Well, the system needs to know, hey, I was inside bash, and I had printed a prompt, and the person typed main and hit enter, and so I made a call to their main function. And once I'm done with that main function, I need to come back to where I was in bash and, you know, print out a new line and print out another prompt. And this is a stack-like structure. So when the code for malloc says return, it needs to go back to the last place that was saved. And each time you make a call, you save the location in your program that you want to go back to. So in our sample code over here, let me put a return down here, and let me put a return up here. So our main program is doing this right here. It's calling malloc. Somewhere the system needs to remember, hey, when you're done calling malloc, come back here and take the return value and set that into this variable sent, and then do this, and then do this. When we call add, we need to remember, hey, when we return from add, we should come back and we should start this second add statement. But when we're inside add, we're going to make another call to malloc. And when we come back from malloc, we don't want to jump up here to this add call. We want to come back to where we were inside this function and say, okay, take the number that we got and set star temp equal to that. So up here when we called malloc, we need to return to this instruction. Down here when we call malloc, we need to return to this instruction. When we call add, we need to return to that instruction. So we don't always return to the same place. And sometimes we nest our calls. We need to remember our previous return values as well as our current return location. Right? And so we need to store multiple return values, and we want them in this last in, first out structure. And so this just begs for a stack. And that's one of the main places stacks are used in computers, is to store return addresses when you make function calls. So if you've done Engineering 270, this is old news to you, because we talk about stacks in 270, and we know that the stack is where the processor stores return addresses every time you make a function call. It stores the program counter of the next instruction on the stack, and when you return, it pops that value from the stack and jumps there. But we can think of this from the level of C as well. And there is a stack-like structure in Unix, and when we make a call from init to malloc, for example, we could actually find a location in memory where all of these return addresses were stored, and this latest return address gets stored after those previous ones. So that's one application of stacks. Another application of stacks in programs related to this is for making local variables. So if I have, integer stuff, and this is some function, I can put, variables in here. And these variables exist only within the execution of this function. If I call another function, these variables are tucked away somewhere. And I could have another function that has variables I, j, k, and they are separate variables from this. And when I return from here, these variables are gone. And if I, had I, j, k in my main program, those are totally separate from these. So these are called local variables. And sometimes those get stored on the stack also. And that's using a stack a different way. That's a case where we would actually be going in and looking at things that aren't just at the top of the stack. And that's actually done by the code generated by a C compiler typically. But it's not using a stack the way that a stack should be used, which is with pushes and pops. But it's taking advantage of this idea that once you push things on the stack, nothing will touch those until you pop. And so what we do is we artificially change the top of stack pointer to create space, and then we use that space to store local variables. And the advantage is when this function returns, we pop the stack past all of that space we reserved, and now the memory we used for these is available for other uses. So that's another place stacks get used. Again, if you've done 270, we go into this in a little more detail sometimes. If you haven't, we'll get to it in 270 and see sort of how this gets set up. And if you take an operating system course or a system programming course or things like that, you'll dig into the structure a little more. If you take a cybersecurity course, you'll definitely get into this. And actually manipulate the stack and look at it and so on and so forth. Well, if stacks are used by things like function calls, meaning that the hardware of the CPU has to know how to do things like push and pop, that's pretty demanding if we implement our stack with a linked list. Because pushes and pops are fairly complex operations for a piece of hardware to do. Imagine trying to build a state machine, like an Engineering 250, that can, you know, allocate memory and adjust pointers and look for nulls and things like that, right? So we need a simpler way to implement stacks if we're going to do this at the hardware level. And so we can also implement stacks using arrays. And so I want to do that next. I'm going to take a 5-minute break first. When we come back, we'll look at implementing stacks with arrays, and this will give us another view of this last in, first out behavior. And then I want to switch to talking about queues. So let's do a break, and let's come back at, let's see, 11:03, 11:08. So we'll do about a 5-minute break. Alright, we're back. Let me make another call out if people want to talk about PA1 questions. We can still definitely do that in class. It's still topical. All right. So let's look at stack implementations with arrays. And so when we implement a stack with an array, we're deciding ahead of time how large the stack is, how many things we can save. And so I'm just going to deal with a stack of integers for simplicity. And so I'm going to make an integer array. I'm going to call it stack, conveniently enough. And I'm going to say this has got space for 10 integers. So this is a integer stack that holds.
About arrays. So when you make an array, you get what will it look like in memory? Is it just like 8 bytes, or what? Right? Is it like 10 bytes in the system, or is it how is it stored in memory?
So when you say integer stack, actually let's do this in GDB. So we'll just make a data array and we'll just initialize it to set the nth element equal to n. So we'll go ahead and execute this. So let's look at data. So if we print data inside GDB, GDB knows that this is an array and it'll show us, the nice values in there. But if we look at the address of data, it's this value, right, which is stored in our stack. If we examine that location in memory, right, we find 4 bytes that are all 0. And then a byte that's 1 followed by 3 bytes of 0, a byte that's 2 followed by 3 bytes of 0, and so on. And so the elements of this array are stored sequentially, one after another, starting at the address of data itself, right, which is this location, turned out to be on our stack. So if we look at more locations in memory there, so there's element 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the next location in memory, who knows what that is? It's something left over, or something that represents something different, or who knows, right? But those first 40 bytes, right, 4 bytes per integer, 10 integers total, those first 40 bytes, that is the data array. And that's exactly how those are stored. There's nothing about this that says this is not part of the array. There's nothing in here that tells us our array ends right here. That's the whole C issue of not having an inherent size to an array. Now if I make this an array of short integers, so our array still looks the same. if I look at the address of my array, it's this. If I say examine 20 hex words at that address, I have a different picture. I now have 2 bytes, right, 4 hex characters that are all 0, followed by 2 bytes, 4 hex characters representing a 1. And then 4 hex characters, 2 bytes representing a 2, and then a 3, and then a 4, a 5, 6, 7, 8, 9, and that's the end of our array now. So now our array is only taking 20 bytes of memory, 2 bytes per integer times 10 integers. And what's stored after that? Well, it's just random stuff. If I do a long int, there's our data array, there's the address. If we look at what's stored there, well, now our first integer 0 is stored in 8 bytes. And our integer 1 is also stored in 8 bytes, like this. And our integer 2 is stored in 8 bytes, and so on. So whatever type of thing we put in the array, they're just, you know, put one right after the other in consecutive memory locations. But we have to know how big these things are to know where the nth element is. If we want element 4, it's going to be at location 4 times the length of a long int, which is 8. So it's going to be 4 times 8 is 32, which is hex 20. So if we take the starting address D0, we add hex 20, we get an F0, that's where element 4 is stored. So this is another way that GDB can sort of help you study what's going on in memory, how things are organized, and so on. All right, so integer stack bracket 10. So we're just going to store plain old ints in the stack, and this 10 is telling me I can store up to 10 numbers in here, and I'm going to draw a picture of this. So here's my stack. And the way I'm going to implement the stack is I'm going to grow my stack downward in this direction, and the top of the stack I'm going to draw at the bottom of my page. So I'm going to draw it at, you know, larger indices in my array. Alright, so we need to know where the top of the stack is, and we usually represent this with something called a stack pointer, sometimes called SP. And terminology wise, when we say top of stack, we usually mean the thing at the top of the stack. So if we have a stack of books, the top of the stack would be the book on the top. But the stack pointer tells us where the top of the stack is. So SP tells us where TOS is. Top of the stack is usually the thing. At the top of the stack. So mostly we're going to talk about the stack pointer. And so if I want an empty stack, I have a choice of how to set up my stack pointer. So I'm going to set this up as follows, and there's going to be several other ways we can do this, but I'm just going to pick this one at random. So initialize my stack pointer equals 0, and that means I have an empty stack. Alright, if I set my stack pointer to 0, what I'm saying is, you know, the first thing that I push onto my stack, I'm going to store right here. Stack pointer tells me where my next push should be saved. So stack pointer is index for the next push.
The index of the next open place in the stack, or the index of the top of the stack?
It's they're kind of the same thing, but let's think of it specifically as the index in the stack where I'm going to store the next thing. So it's basically the next open spot in the stack or in the array. And it's close to where the top of stack is. The top of stack will actually be one spot before that.
Yeah, that's good number.
Okay. So I'm going to use SP as the index for the next push. So if I say something like push, so my stack pointer equals 0. If I say let's push a 2, I'm going to store that 2 at index 0 in my array. So I'm going to put a 2 right there. And I'm going to increment my stack pointer to be 1. So now stack pointer still tells me where my next push should be saved. So if I say push 18, I'm going to look at the stack pointer, it's a 1, I'm going to store my 18 right there at index 1, and I'm going to increment my stack pointer. And now if I want to push a 45, I'm going to look at the stack pointer as a 2, I'm going to store my 45 at index 2, and I'm going to increment my stack pointer. Alright, if I did another push, pretty clearly it would get stored right here at index 3. But if I do a pop, what value should I pop right now? I should pop off this 45. Well, the stack pointer is equal to 3. So to pop, the first thing I want to do is decrement the stack pointer and then give you the number that's stored at that index. That's a 45. And after I've done that, the stack pointer is 2. Well, this is now the spot where the next push would take place. So if I were to push something after doing a pop, right, so the pop gives me back a 45. If I were to do another push, it would get stored right here where the 45 had been. If I do another pop, I'm going to decrement the stack pointer, make that a 1, give you back the thing at location 1, that gives me the 18. So I popped off the 45, I popped off the 18.
So is stack pointer supposed to like keep track of how many things are in the array stack?
That's the other interpretation of the stack pointer. The stack pointer equals the number of items on the stack. Excellent. So when the stack pointer is 0, there's nothing on the stack. That's an empty stack. Right now the stack pointer is 1. Well, we only have one thing left on the stack. That's a 2. And if I were to push something at this point, let's push a 5. Well, the stack pointer is 1. I'll put a 5 right there, and I'll increment the stack pointer. Well, there's the first thing that's on the stack, a 2, followed by a 5, and the stack pointer is 2, tells me there's 2 things on the stack, and 2 is the index where I would store the next push. And by the way, we have again this this security issue where we popped off a 45, but guess what? That 45 is still sitting in memory. when we popped it off, it didn't disappear from memory. We just stopped referring to it. Now, if I push something else after the 5, it'll overwrite what's at index 2, and the 45 will be replaced. But at the point where I simply popped off the 45, that was still sitting in memory. And when I popped off the 18 was still sitting in memory until I overwrote it by pushing something. And this is another security concern. Because since we're using the stack to store local variables, if a piece of a program does something like, manipulate a user password or a credit card number or a social security number, and those local variables are stored on the stack, when the function exits, those variables might still be sitting in memory. And another program can come along and access those same locations in memory and read the local variables that were being used by a totally different function, maybe a totally different process.
Actually, update. Can you use the key as a free function to free the 45 if it's not being pointed anymore?
Well, free is only for things that we've malloc, and with an array that wouldn't work. But we could do something like that. We could modify the pop function to say, hey, after you record the value that you're going to return, let's replace that with a 0, for example. And that would, help take care of this particular issue. But that's a performance hit too. And unless it's really important that always happens, most pop functions won't necessarily do that. And so these are things that, as a C programmer, you write a function, you've got local variables, you do stuff, your code looks perfect, but from the perspective of the operating system, or maybe the computer architecture, right, there's these potential vulnerabilities out there. There's potential performance issues out there. There's all kinds of aspects of computer science that we need to be aware of, even if we think of ourselves as just a software person. I'm just going to write C code. That's what I'm going to do. Well, if you don't understand computer architecture, you're not going to write the most efficient code possible. If you don't understand operating systems, you're not going to write the most secure code possible, right? And so this is why, as computer science majors, you take courses like, Engineering 250 and Engineering 270, Digital Logic and Microprocessors, and you'll take an operating system class, and you'll take, all these other courses that may seem to have nothing to do with programming, right? But it's because you kind of need a holistic view of the entire system, hardware, software, connecting fabric, to be able to do some things as well as you might hope to do them. So that's just kind of an example of that. Alright, so how would we code something like this? It's not too hard if we keep straight this picture. So SP equals 0 equals next push location. And my stack is growing in this direction. The top of the stack is at the bottom. Alright, so what does my push function do? Push n. So I want to use my stack pointer for the location to save the thing I'm pushing. So stack bracket n, stack bracket SP equals n.
Like pass the array or something like that?
Yeah, let's. You would have to give it the stack array somewhere. But I'm going to assume this is a package, and the package has access to the stack array. So that's like declared inside, an initialize function, for example. But if you wanted to work with multiple stacks, yeah, you'd want to pass a stack to it. when we get to 223 and we deal with objects, the question you asked will be extremely topical. And in fact, what we're going to do in 223 is we're not just going to take the data corresponding to some structure. We're going to take the code that manipulates that data. We're going to bundle it all together into a single thing that we're going to call a class or an object. And once we do that, we'll simply have an object called a stack. A class called a stack will create an object which is an implementation of a stack, and it will come with a push and a pop and an isEmpty and things like that. And it will also contain the memory that we use for this implementation of the stack. And we'll get away from having to do things like with our linked list code passing both the sentinel node and the number we want to add. We'll be able to just say add this number, and the structure will kind of come along for the ride. So that'll make more sense in 223. Alright, so to push n onto the stack, we basically need to save it in our array at the location given by the stack pointer, and then increment the stack pointer. That's the whole push function. And if we want to be more succinct, we can do this. So this is a post increment operation. If you're not familiar with these or don't remember these from C, go back and play with those in some code. This says use the value of SP. So this will access element SP from the stack array, set it equal to n. But after it's used SP, it will increment it. So it basically does this, followed by this. Our pop function can just return stack bracket minus minus SP. We can do a pre-decrement. So this says subtract 1 from the stack pointer first, and then use that as an index into stack. Take the value you find there, return that. So pop function, very simple too. And we have shamelessly ignored the question of what to do if errors occur. So when you're popping, if your stack is empty, SP equals 0. If I try to execute the statement, this is going to subtract 1 from SP. SP is going to be -1. I'm going to index my stack with an index of -1 and try to return that value. So I'm going to be trying to read, something that's stored at this negative first element of the stack. And that's, at least random data, at worst a seg fault. So stack underflow, who knows what's going to happen. If my stack is full, let's say my stack can hold 10 integers, my last index is 9. If my stack is full, SP will be equal to 10. And when I try to push, right, I'll use the current value of stack pointer 10, and I'll try to store my n there. Well, now I'm trying to store in this non-existent 11th element of the array. And that will either give me a seg fault, or it will, write my number into some location that may be being used by something else. That may be a local variable x. And now by pushing a number on my stack, I've changed the value of a local variable. So is empty we just have to check to see if the stack pointer is equal to 0. If the stack pointer is 0, the stack's empty. And then our isFull function for this example we would want to know if the stack pointer was equal to 10. And if it is, then the stack is full. It's not an error condition yet, but there's no space left in the stack because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things stored in there. Every spot is in use. So ideally, you know, in your push code before doing this, your code should check to see if the stack is full. And if it is, do something different. And before you do this, check to see if the stack is empty. And if it is, do something different. But that depends on what you define your stack package to do with error conditions. All right, questions so far?
Yeah, I'm taking notes right now. What would you call things inside of the stack an element, or what's the specific name do you give them?
Yeah, you could say stack elements. I've been calling them elements, I think, because I think of members of an array as elements. But it's just stuff on the stack. I think that would work too. Yeah, I don't know if there's a particular preferred name for those. And really, most of the time, unless it's at the top of the stack, we kind of don't think about what's on the stack. Because if we're just using pushes and pops, right, all the action happens down here at the top. All right, so this description that I just gave, where this is our push and this is our pop, there are other ways to do this. So for example, we're using the stack pointer to tell us where the next push should take place. We could instead do something like SP equals location of the next pop. Well, what would that mean? We would initialize the stack pointer to be -1. And that would be our flag telling us there's nothing on the stack. And now our push function would want to do something like stack bracket plus plus SP equals n. In other words, we would want to increment the stack pointer first and then use that as an index. So if we initialize to -1, the first time we push something, stack pointer gets incremented to 0, and we change our first number at location 0. And our pop would return stack bracket SP minus minus, because SP is the location of the next pop. So we'll return the element indexed by SP, but after we've read that element, we'll go ahead and we'll decrement SP.
Does it matter where you put the 2 pluses and the 2 minuses, like whether or not they're before or after the...
Yeah, so they do very different things, and I'm glad you asked. Let's actually do this. I've never done this in class before, and I should. Which means it might break fabulously. Alright, so let's try both of these things. Let's set I equal to 5, and let's print out the value of I++, and then print out the value of I. And then let's again set I equal to 5, print out the value of plus plus I, and then print out the value of I.
Don't you need an ampersand in front of the single eyes? For the
Ampersand is scan F. That's
Yeah, ampersand would be for scans. I don't think we need it for prints. But let's see, if it blows up and crashes my machine, we'll know.
Well, no, because you drop out of the call.
That's right, that too. Alright, so let's run this, right? So I initialized I equal to 5, and then I printed I plus plus, and it printed a 6. Sorry, it printed a 5. Right, and after that statement was done, I was equal to 6. So I got incremented, but it printed the value prior to incrementing. When I said print plus plus I, it printed out a 6. And afterwards, I was equal to 6. So both of these statements will increment I, but the question is, when does the increment take place? With this statement, the increment takes place after you use the value. So this says, you know, take the current value of I, which is 5. Okay, that's what we're going to print. That's where it printed out, you know, this is equal to 5. And then after you're done using I, go ahead and do the increment. Set I to 6. The plus plus I is a pre-increment. And that says, hey, we want to use the value of I, but before you use that value, let's increment it. So it takes the current value 5, increments that to a 6, and the 6 is what gets sent to this %d, so it prints out plus plus I equals 6. So subtle but important difference. Now if all you want to do is just, you know, set I equal to I plus 1, makes no difference. You can do I plus plus or plus plus I. But if you do something like, you know, x equals 5, sorry, I equals 5, x equals plus plus I, right? These will do very different things. At the end of both of these, I will be equal to 6, but this will set x equal to 6 because it says increment I first. This will set x equal to 5 because it says increment I after you've used it. So that's the pre and post increment business. And exactly the same thing for minus minus for pre and post decrement. So in the case of stacks, it's definitely making a difference, right? The stack that we first used where SP was the location for the next push, we're using that value to store our number before we increment it. But in this value where we're using SP for the location of the next pop, we're going to push by incrementing the stack pointer first and then using that as the index. And then to pop, we use the current value of the stack pointer and then we decrement it. Alright, so there's two different ways we can implement a stack with an array. We can implement with a post-increment stack. We can implement with a pre-increment stack. And both of those have the idea that, you know, an empty stack has nothing in it. The first thing we're going to save is at index 0 and our stack's going to grow in this direction. But we could do something totally different. We could make our stack grow in this direction. And we could initialize our stack pointer to 9. And we could say SP equals next push loc. And if we say push a 5, we could put that 5 right here and change the stack pointer to 8. And then if we say push a 12, we could put that at the stack pointer location and decrement the stack pointer to 7. And so now we have a post-decrement push function where our stack pointer decreases, and so our stack is basically growing towards lower indices in our array. And we could do a pre-decrement push, and that would be a fourth version. And so in general, when you're working with stacks, you'll see lots of different different specifics on how these are implemented. The pick on the 270, I think, does a post increment push instead of a pre. And the 270, the pick processor stack starts at element 1. They don't actually use element 0. It's just, I mean, there's all these variables you can make to this. Most operating systems have a stack that grows in this direction, and they put the top of the stack at, you know, this address right before the halfway point of memory, and then they grow in this direction. And they do that because usually the code for your program starts, you know, somewhere close to memory location 0. First few spots are reserved, and the program, the longer it is, you know, grows in this direction. And by starting these at kind of opposite ends and growing the stack towards the middle, right, you minimize the chance of your stack colliding with your code. But you still allow programs, computers, to have, you know, large amounts of memory available, and you just say, oh, I'm just going to start this at this really high address and grow in that direction. So you'll encounter stacks in lots of different situations: computer architecture and programming and algorithms and so on and so forth. See, PA1 question: what's the syntax for calling the init function to set up your Sentinel node? So yeah, somebody posted the answer in chat. So make a struct my node. Make a pointer to it called mylist. And when you want to initialize, mylist equals init. And you can do this on one line if you like, or you can do it in 2 separate lines. But yeah, you're calling the init function, you don't pass any arguments to it, and the thing it returns, that is the address of the Sentinel, so just mylist equals init. That works great. And thanks for posting that in chat. Alright, got the basic idea of stacks?
Yeah.
Yes, sir. Alright, let me show you one other thing that stacks kind of come in for, and this is something you'll do in an algorithms course. Let's suppose we have a maze. I am really horrible at like drawing mazes on the fly, I've discovered. But I'm trying anyway, apparently. So let's say we've got some maze, right? How do you solve a maze? You know, if you start at the beginning, you basically go down until you get to a decision point. And right here, I can go, you know, left, or I can go straight. Well, maybe you go left, and now you come to a point where you can either go left or you can go straight. Well, you go left, and you hit a dead end. And most people will back up to the last decision they made, which was right here, and say, well, going left didn't help. Maybe I should go straight. And so you'll go straight, and you'll go left, and go right, and go left. And you hit another dead end. And now you're going to back up to the last decision that you made, which was, you know, here you had no choice. You had to go left. And so you come back all the way over to here, and you say, okay, well, I went left here. Maybe I should go straight. And you come down, and you start exploring. And you get to a possible branch here, and so you try turning, and so on. And so this is, again, you know, a stack-like structure. We just hug a wall, yeah. We you know, put a finger down where we make a decision, and then we choose, one way or the other, and we go on. And if we get stuck and we can't follow any paths on that, we go back to the last finger we made. If we had a decision to make here, we put down another finger and we follow it, and if we have to backtrack, we come back to that last place we marked, make a different decision, and if there's no more decisions to be made, we go back to the previous spot before that one. And if we get to the end and none of this has worked, then we may come all the way back to the start and say, okay, instead of going straight, let's go to the right. And we follow that and it takes us out or something. And so that works with a stack. We can do this with a different kind of structure that we're going to talk about next, called a queue, but it doesn't feel natural for most people. It's probably one of those 90-10 things, right? Probably like 90% of the people function with stacks more naturally than this other thing, which is called a queue. This is also how we do things like surf the web, right? So you're looking up the programming assignment for 222, right? And you open your browser and there's Google News and it's got a headline about something, outrageous. And so you click on that and you start reading the story, and it talks about something bizarre that somebody said, and so you click on that person's name and it takes you to another page that tells you about this person's background and such. And the browser is using a stack to keep track of where you were each time you go somewhere else. And when you hit the back button, it doesn't take you back to the place you started, it takes you back to the last place you were when you jumped to another page. And when you are done reading that page, if you hit the back button, it'll take you back to the last page you were on before you got to that page. And it's another LIFO structure. So your typical browser, if you follow links to go from one page to another, and then you use that back arrow button, that's using a stack structure. And it kind of goes along with this idea that we tend to kind of spread out multiple tasks using this same kind of stack storage. Let's see, PA extra credit idea, procedurally generated mazes. Maze generation is fun. It's really freaky to do that. That would be fun. Hug a wall, topology for the win, yeah. Or bulldoze through the walls. Nice. Alright, so the kind of counterpose to a stack is what's called a queue. And a queue, instead of being a LIFO, it's a FIFO. So it's first in, first out. So a queue we can picture, sort of a line or a corridor or something like that, maybe, two ropes marking off an area on the sidewalk, and people arrive at this end and they move to the head of the queue. So this is the head, and they enter the tail of the queue. So let's say person A arrives, they're going to move up to the head of the queue. And then person B arrives and they go behind person A, and person C, D, and E arrive. And now you have 5 elements in this queue. Okay, the first thing to enter the queue, which was A, is going to be the first thing to remove from the queue. So this is a rope line outside the entrance to the very exclusive programmers club, right? And somebody finishes their meal and they leave, and there's space for somebody to come in now, so the bouncer lets the person at the head of the queue into the club. And so A gets removed from the queue, and now B, C, D, and E move up. So the second thing to enter the queue, B, is going to be the second thing to leave. And it does not matter if, you know, a bunch of other entries are loaded into the queue, B is still going to be the next thing removed. And when A was the first thing in the queue, it didn't matter how many things were in the queue behind, A was going to be the first thing removed. It's in some sense the exact opposite of a stack. If this was a stack and H just came in, H would be the first thing to be removed. But in a queue, H is the last thing to go in, so it's going to be the last thing to be removed. So it's kind of like a LIFO. And the first thing in the queue, B, right, that's the most first thing that's been in the queue, that's going to be the first thing to be removed. So it's got this first in, first out behavior. Let's see, is a linked list also known as an associative array? No, so an associative array is something very different. We played with them in Bash in 224, and it was the idea of an array that you could index with things other than integers. So we could make an associative array called, you know, data, and we could say data bracket 2, data bracket 5. We could also say data bracket Nick, data bracket hello world. And, you know, Nick or hello world or things like that could be valid indices used to address elements in this array. And so we use that to store words that we were going to tally in a tally program. What query should a querier use to queue up in a queue? Good question. How much wood? Woody woodchuck chuck. All right, so first in, first out, and so we don't do push and pop. We usually think about like add and remove. And so add is putting something into the queue, and remove is taking something out of the queue. And terminology, this is fairly standardized, not 100% though, but we'll be totally standard about this in this course. Add is always done, add to the tail. And when we remove, we always remove from the head. So with a stack, the end of the stack is, you know, the top of the stack. With a queue, there's two ends to the stack. There's the head and the tail. And the standard we're going to use is when you add things, you put them in at the tail end. When you remove from the head end. And if you get those reversed, then everything will seem backwards compared to what we're talking about. All right, so examples. Here's our queue. Here's the head. Here's the tail. So let's add a 5. There we go. Let's add a 10. There's a 10 sitting in there. Add an 18. There's an 18 sitting in there. Let's remove. So the 5 is going to get removed from the queue. And now this is going to be a 10, and this is going to be an 18. If I were to say remove again, I would remove the 10. If I say add 11, then 11 goes in behind the 18. If I add a 20, the 20 goes in behind the 11. If I say remove, that removes the 10 and everything moves up. If I say remove again, that'll remove the 18, we get an 11 and a 20. And if we say remove again, we get the 11 and the 20 moves up. And if I were to say remove one more time, I'm going to get the 20. Why am I getting the 20? Because that's the last thing that I added. Why did my first remove give me a 5? Because 5 was the first thing I added. Right? So the first thing in is the first thing out. And the last thing in is the last thing out. But again, FIFO is sort of the standardized terminology. Alright, so you got the idea of a queue? And you know, think of a line at the grocery store, or a line to get into a movie or something like that. Or, you know, if you do in-person classes, the line in which you enter your classroom single file. That's a queue. And your queue can be empty. You know, I open the door of the classroom, there's nobody there waiting to come in. That's an empty queue. The queue can also be full if you know, you have, you know, ropes marking off a section, and every spot in here is occupied, and somebody new tries to join the queue. Well, they would have to go, you know, outside the physical boundaries of the queue, and so the queue could be full. And if you try to add to a full queue, that's an error. If you try to remove from an empty queue, that's an error also. Alright, somebody asked about pseudocode for the search function. I don't remember if we've actually done that in here. I know we did it in the B section yesterday. But search is very much like print. So we spec'd out a print function. Which we pass, you know, a sentinel to. And so it's something like temp equals sentinel next. This should be next node, but I'm just going for pseudocode here. So I'm going to look at the next node, and I'm going to say while that node exists, so while temp is not null. And we do two things: print the data in the current node, and then move down the list. And I'm pretty sure we've done this pseudocode before. So that's for the print. So if you want to do a search, it's almost exactly the same algorithm. But instead of doing a print, let's just look at the current node's data and see if it equals n. So if temp arrow data is equal to n, well, guess what? We found our number. We can just return a 1 right there. And if we get all the way through our while loop, we get to where the current node is null. If our number is not in the list, this will never have been true. We will not have returned. And the only way we'll get out of our while loop is if we hit the end of the list, never having returned. Well, if that happens, the number's not in our list, and at that point, we can just return a 0 saying, sorry, didn't find your number.
If it returns 1, wouldn't it also return the node in which that number is stored? Or is it just, is search just to be used to check if there's even an instance of that number?
Yeah, search is purely a binary thing. It's either is the number in the list or is the number not in the list. It doesn't actually tell you where it's stored. But that would be a useful function to have, right? Because then you could use that in like your add or your delete function. So you could make, you know, a different version of search, like, you know, my search, for example, that might somehow do that, and use that inside add or delete as you like. But the actual search function specified in those 6 functions should just return a found or not found flag. How do you display the data stored in the node without changing the position of the node in the linked list? Not sure what that means, but displaying the data.
I was basically asking about if we just did that. So
Okay, okay,
well,
cool. All right, well, not surprisingly, we can implement a queue with a linked list. And so let's start off with, you know, an empty list. And let's add a 10. So I'm going to put a 10 into my linked list. I'm going to add a 20. I'm going to put a 20 at the end of my list right before this last node. So I'm going to make my sentinel point to a 20 and then point to a 10. I'm going to add a 30. Let's see. Forget that for a second. Let me do this the way that I want you to do it in code, if I give you code. There's two choices. We can add at the beginning of the list or at the end of the list. Let's do them both. Add at the start, remove from the end. So we'll think of our linked list as being a tail over here and a head over here. Alright, so if we add a 10, we'll point to that. If we want to add a 20, we'll put a 20 in the beginning. So the sentinel will point to 20, which points to 10. If we want to add a 30, we'll put a 30 in the beginning. And this looks exactly like the add function, the simpler add function, or the push function that we did for a stack. The difference is when we remove, we're going to remove from the end of this list. So if we say remove, we'll remove this 10, right? We'll return the 10 value and change the last node here to point to null. And then when we remove again, we'll give you the 20. So this returned to 10, this returned to 20. And then when we remove a third time, we'll give you the last node, which is a 30. So the remove is happening in the same order as the add. That's the FIFO behavior. And anytime I add something to my queue, it gets pushed here in the beginning, but I'm removing from the other end of this list. So if this is the thing that's about to be removed, it doesn't matter how many things I add before that. When I eventually say remove, guaranteed it's the 10 that's going to come out. All right, but there's a slight issue with this particular implementation. So adding, very easy. Just insert something right after the sentinel node. That's order 1. But to remove a node from the list, I have to get to the end of the list. I'm deleting from the list, but I'm not deleting a particular value, I'm deleting a particular position, in this case the last thing on the list. And so I have to move from the sentinel all the way down the list until I get to something that points to null, the last thing in the list. And I have to remember what the previous node was, and then basically change the previous node to point to null. And so this is going to turn out to be in order n. But if instead I put the head of the queue next to the sentinel, and I put the tail at the end of the list, and I say add at the end, remove from the beginning, life gets a little better. So here's my sentinel, I add a 10, that's going to point to a 10. I'm always going to add at the end, so I add a 20, that's going to be a 20, I add a 30, that's going to be a 30. And now to remove, I just remove the thing the sentinel points to. So I would look at the sentinel, let's say it's pointing to a 10, I'll return that value of 10, and I'll change the sentinel to point to what the sentinel's first node was pointing to. So if this was pointing to 20, I'll change the sentinel to point to a 20. So the remove is definitely order 1. It's all happening here, it doesn't matter what else is in the list. At first glance, the add would be in order n because I have to get to the end of the list in order to add that new node. But I can have a separate variable called end of list that always points to the end of the list. And when I want to add something, all I do is follow end of list to this node, put my new node on here, change end of list to point to that, and update end of list to point to the new end of the list. And so if we do it in this order, the adding can also become order 1. All right, questions. We've got a lot more to say about queues, but that's probably as far as we're going to go today with queues. All right, somebody asked in chat, does the sentinel node have to be called sent or does it matter? The only requirement I have is in your main program, I want your sentinel to be called myList. So main node structure is this: declare a sentinel node pointer in your main program as follows: struct mynode star mylist. But inside your linked list functions, you can call it whatever you want. You can call these arguments whatever you want in your prototypes and in your function code itself.
Would that affect the pointer won't that affect where the pointer points to?
Won't what affect it?
If you call the sentinel node something other than mylist in the linked list functions or whatever, run that?
No, so if you make a print function and you call the argument list, that's totally fine. When I call print, I would have to say print parentheses mylist, right, in my main program, because that's the name of my sentinel node. But inside my print function, if I say that my argument is called list, as long as I use list inside that function code for print, that should work fine. If I call it sent, that should work fine. Right, so the name isn't important, it's strictly positional. So if I call print and I give it an argument of my list, whatever I call this variable, it'll be equal to my list. Does that make sense?
So the sentinel node is the last node in the list?
Sentinel node is the thing that points to the first node in the list. And it's this trick that we do. If you have a list containing 3 numbers, 10, 20, and 30, there's always this extra node we don't really see called the sentinel that points to the 10. And this is the thing that we use to refer to the list. This is the thing we would pass to the print function and so on and so forth. But we understand that, even though this has a data field, which is 1, 2, 3, 4, 5, 6, 7, it's not actually part of the list. It points to the actual first node in the list. And it's this convenience trick so that if we have an empty list, if we delete the 30 and the 20 and the 10, we still have the sentinel node. But it points to null, and that tells us, oh, there's actually no data in the list.
Two more things. One, when we declare the sentinel node, I'm assuming we declare it right after the struct my node.
Mm-hmm.
And
Yeah, declare it in your main program. So this goes outside of your main program, right? I mean, it could go inside, but if you have other functions, you usually put this like in the beginning of your main.c, or for us inside the main.h. But then the declaration of a struct my node star my list, that goes in the top of your main program. Right, so that would go in your main program. This goes outside of main.
Okay. Lastly, the Sentinel node, when you declare it, you have to, you also have to set its data value equal to 1, 2, 3, 4, 5, 6, 7, right?
Mm-hmm. Correct. And that happens inside your init function. So your main program says mylist equals init paren, and init should set the next node field to null and the data field to 1, 2, 3, 4, 5, 6, 7. All right, we're a little bit over time, so I'll call it good there. So thank you everybody, and come by office tomorrow morning. I'll be in from 8 to 10 if you have questions on this. And then Monday we will continue looking at queues, this implementation with a linked list, and we'll also look at implementation of a queue with an array, and that'll get us into circular buffers, which is a generally useful structure to work with. So we'll keep building on that. All right, have a great afternoon. If I don't see you in 2:15, I'll see you next week. Take care. Thanks.